Okay.
Okay. Well, today we have Wei Xing from Uppsala University, who is going to talk about a derived equivalence for higher Auslander algebras of type A. Thank you very much, Wei, for accepting our invitation, and start whenever you like.
Thank you, Javier, and thank everybody for having me here. So I would like to present a derived equivalence for a class of path algebras of quiver with relations, and they're called higher Auslander algebra of type A. And so oh, in the talk today, there are three parts. So firstly, I will give some background on higher Auslander theory, and which was started by Iyama in the mid-2000s. And then I will introduce the definition of higher Auslander algebras of type A. And these algebras were constructed also by Iyama in the framework of higher Auslander correspondence. And after that, I would introduce the main result and also some further observations obtained, like further corollaries that can be deduced from our main result. Okay, so let's start from the background. We fix K to be a field, and we consider finite dimensional right modules. So the main object to study in higher AI theory is the subcategory which is called d-cluster tilting. So if we fix D to be a positive integer, and we take C to be an abelian category or a triangulated category, then subcategory M of C is called d-cluster tilting if it is functorially finite, which means that for the object in C, there exist left approximations and right approximations by objects from M. And in the case when C is abelian, we also want M to be generating, co-generating. Moreover, the following equation holds true for the subcategory M, meaning that M consists exactly the object C from the abelian category C, in which this extension vanishing condition holds true between objects C and objects in M, like both from the left and from the right. So in particular, since M consists the object that satisfy this condition, in particular, the first d-1 extension group between objects in M vanishes. So that means M satisfies certain kinds of rigidity property. And also M is sort of like maximum with respect to this rigidity property. If moreover, the non-vanishing extension group between objects in M only appears in the degree which is the multiple of D, then we call M a DZ cluster tilting. So this notion, if C is a triangulated category, then a DZ cluster tilting subcategory is turns out to have a so-called D plus 2 angulated structure, which is the generalization of triangulated structure. So if we restrict to the module category, then a module M is called a D cluster tilting if the additive closure of M is a D cluster tilting subcategory. So so from the definition of d-cluster tilting subcategory, it's not necessary that this M has an additive generator. But when we say that a module is d-cluster tilting, that means that the additive closure, this d-cluster tilting subcategory, has an additive generator. So this is the main object that we care about in higher Auslander theory. And For example, when d equals 1, if we look at the condition here, then this extension vanishing condition would be empty. So that means M equals the whole module category. So exactly the one cluster tilting subcategory of a module category is the module category itself. And in this case, there exists a one cluster tilting module in the module category if and only if mod A has an additive generator. In other words, that means A is representation finite. So we can see from this this simple example that having a D cluster tilting subcategory is actually a very restrictive condition. That in general, if we pick up a random finite dimensional algebra, it's difficult to tell if there exists a D cluster tilting or not, or it's difficult to give a full classification. Yeah. And let's look at a more complicated example. If we take A to be the path algebra, which is in which the quiver is just a linear A3 quiver, and the relation is generated by the zero relation beta alpha. In this case, we can draw the Auslander right-hand quiver of A, which looks like this. So the projective modules are given by 1, 2, 1, 3, 2, and the injective modules are given by 2, 1, 3, 2, and 3. So if we take M to be the direct sum of the four modules, the four indecomposable modules, it turns out that M is a two cluster tilting module of A. So again, if we look back this extension vanishing condition, if C is a module category of a finite dimensional algebra, the first vanishing condition tells us that the projective modules must contain in M, and the second one tells us that the injective modules must contain in M. But of course, there might be non-projective, non-injective modules in M as well. But in this special case, if we just take the direct sum of projective and injective modules, this M is already a two cluster tilting module of A. So why do we care about such subcategories? That's one of the motivations because of the higher Auslander correspondence. So we call a finite dimensional algebra gamma a d-Auslander algebra if the global dimension of gamma is at most d+1, and the dominant dimension of gamma is at least d+1. So you can think that the dominant dimension of an algebra is sort of a measurement to compare how far is this algebra being self-injective. So a self-injective algebra has infinite dominant dimension. Okay, so oh, sorry. So the d-Auslander correspondence stays as follows. So if we take a finite dimensional algebra lambda, and lambda should be A. If you take A to be a finite dimensional algebra and M to be a d-cluster tilting module, then the endomorphism algebra of M would be a d-Auslander algebra, which means that the endomorphism algebra has this special homological property. And moreover, Iyama showed that any d-Auslander algebra gamma can be obtained in this way. So indeed, this gives us a bijection between the sets of equivalent classes of d-cluster tilting subcategories and the Morita equivalent classes of finite dimensional d-Auslander algebras. Yeah, that is one of the main motivations of studying d-cluster tilting subcategory, and yeah. So one last thing I want to recall is tilting complexes, since the derived equivalence I'm going to introduce is introduced by a tilting complex. So if we, again, A is the finite dimensional algebra, and we denote by KB of A, the bounded complex of finally generated projective modules, then a complex T is a tilting complex if, so firstly, it belongs to KB of A, and the home space from T to any non-zero shift of T would be 0. So this is some sort of rigidity property again. And lastly, T generates KB of A as a triangulated category. So so a tilting complex is sort of a generator of the ambient category, which has nice rigidity property, roughly speaking. Oh, sorry. So well-known theorem that if we have an algebra A and tilting complex T, then there's a derived equivalence between A and the endomorphism algebra B of T. And the functor is given by the derived home T, which sends T to B. Okay, now we're ready to introduce the main object for today. They're called higher Auslander algebras of type A. So as we have seen the definition of Auslander algebras, they have nice homological properties, and of type A because they can be constructed by linear AN quiver. Moreover, there's a very nice combinatorial description of this class of algebra. More precisely, the d-1 Auslander algebra, which I denote by AN of D of type AN, is given by a path algebra of quiver with relations. And the vertex set of the quiver is given by the ordered sequence of cardinality D, in which that this ordered sequence, they are strictly increasing, and they land in the range between 1 and n plus D minus 1. So you can view it as a pole set if you want. And the arrows are given by such arrows from x to sigma s of x, where x itself is an ordered sequence, and sigma s of x is also an ordered sequence. It is almost identical to x, except for that they differ in one coordinate by 1. So since the vertices are given by ordered sequence of cardinality D, and from the definition of the arrow, you can imagine that starting from one vertex, there are D possible ways of the direction of arrows that coming out from this vertex. But well, later we'll see a more explicit example. And moreover, the admissible ideal is generated by the commutative relation given as follows. But since there's restrictions on the ordered sequence, so sometimes sigma s of x is not always defined. So sometimes this commutative relation would collapse to 0 relation. Okay, so there are a lot of data. But let's look at an example. If we take D to be 1, then the vertices of this quiver is given by order sequence of cardinality 1, which in this case is just 1, 2, 3, 4. And the arrows are just given by 1 to 2, 2 to 3, and 3 to 4. So in other words, that AN1 or A41 in this particular example is just the linear AN, the path algebra of linear AN quiver. It is well known that A is representation finite, which means that there is an additive generator M in the module category. And in the language of cluster tilting, M is called a one cluster tilting module of A. So, so we can calculate the one Auslander algebra of A, which is the classical Auslander algebra. And it turns out to be A42, which is the path algebra given by the following quiver with relations. So like according to our definition, that A42, the vertex of this quiver of A42 consists of those ordered sequence of cardinality 2. And the arrows are given by, for example, from 1 to 2, 1, 3. It's like 2 added by 1, you get 3. So there's an arrow here. But if you add 1, and then you get 2, 2. But since 2, 2 is not strictly increasing, it's not defined. So we lose that arrow. So, and also the relations are given by the commutative relations of all the squares. And sometimes it collapses to a 0 relation. And in this case, it is the 0 relation of all the half squares at the bottom. So, so if you look at this example, you start from linear and quiver, you take the additive generator, you take the endomorphism algebra, and then you get one Auslander algebra of type AN. And you might want to iterate this process to get more, right? And indeed, it turns out that A42 has a 2 cluster tilting module, which we'll introduce later. And if you take the endomorphism algebra of this 2 cluster tilting module, we would get A43. And A43 is again a path algebra given by the following quiver with relations. And again, the vertices are ordered sequences, and the arrows are given as follows. And and all the squares are commutative, and there are also 0 relations of half squares. I just labeled some of them and omit the rest of it. Okay, so we have seen enough examples. Let me summarize the homological properties of A and D. So for arbitrary N and D, there exists a DZ cluster tilting subcategory, which I denote by M and D. And this DZ cluster tilting subcategory admits an additive generator, M and D. In this case, M and D is a DZ cluster, is a DZ cluster tilting module of A and D. And it is the direct sum of all the modules of the form M of X, in which X is a ordered sequence of cardinality D plus 1. So I'm not going to give like a rigorous definition of MX, but we can look at an example here. So if again we consider A42, which is the path algebra of the quiver given on the left. If we take X to be 135, for example, we can associate a module M of X. How do we do it? The so-called of MX is given by the simple module at vertex 1, 3, which we can read from X. And the top of MX is given by the simple module at 2, 4. Well, 2, 4 can be obtained by 3, 5 by subtracting 1 from each of them. So M of X is indeed this representation in which we put a one-dimensional vector space on each of the vertices between 1, 3 and 2, 4. And all the maps would be identity maps. Yes.
Sorry, why are the arrows reversed in the MX?
Yes, because here we consider right modules. So the representation is actually like the representation of the opposite quiver.
I see.
Yeah. Yes. So these modules, this kind of module MFX are those kind of like box. They look like a box. That from this X you can read its circle and its top and every other vertex in the middle. You just put a one-dimensional vector space there and get the representation. Okay, so it turns out that AMFT is the endomorphism algebra of MND minus 1 over AND minus 1. So it means that it really deserves the name that AND is a D minus 1 Auslander algebra of A and D minus 1. Yeah. And so moreover, the global dimension of A and D is equal to D and equals to the dominant dimension of A and D. Yeah. So now I'm ready to state the main result for today. So we fix A to be a d-Auslander algebra, a n plus 1d, with the condition that n, d are co-prime. And let P be a certain basic projective A module, which we will introduce later. And we denote by nu the Nakayama functor from on dB of A. So T is the direct sum of nu I of P, where I goes from 1 to n plus D. And we take B to be the endomorphism algebra of T. Then it can be proved that T is a tilting complex. And so there's a derived equivalence between A and B. And moreover, we can calculate the global dimension of B, which equals n times D. So remember that the global dimension of A is D. And the global dimension of B is, of course, finite, because the finiteness of global dimension is a derived invariant, but it's much larger than the global dimension of A. And moreover, if you take the direct sum of projective and injective modules of B, we get an ND cluster tilting module. And also B has this fractionally Calabi-Yau property. But this because A has a fractionally Calabi-Yau property of the same fraction. So this is immediate. Okay, maybe it's a bit abstract. Let's look at an example again. So if we take D equals 1, remember that A is just the path algebra of linear AN quiver. And we take P, in this case, to be the simple projective module. There's only one. And we take T to be the direct sum of nu I of P, where I goes from 1 to n. And this can, by direct calculation, that that T is a tilting complex indeed. And this object was implicitly considered by these authors. And if we calculate the endomorphism algebra of T, it turns out that B is actually isomorphic to A modulo radical square of A, which in other words is the causal dual of A. So it is well known that A is derived equivalent to its causal dual. So we can recover this result. If we look at a more explicit example of this example, we still take A to be A4, 1. And then the quiver is just linear A4 quiver. And P would just be P of 1. And T is the direct sum of nu I of P1, where I goes from 1 to 4. And again, as we already mentioned, that B is isomorphic to A modulo radical square A. For D equals to 2, similar results were also obtained by Latkani. Oh, sorry. So if we take A to be A n plus 1, 2, remember that we need the condition that n, d are coprime. So we take n to be an odd number. For example, if we take A42, which is the past algebra of the quiver shown on the left. And in this case, we take P to be the direct sum of the indecomposable projectives at vertex 1, 2 and vertex 1, 3. And we take T to be the direct sum of nu I of P, where I goes from 1 to 5. We need to have like 10, we need to have 10 direct sums of the object, right? So we need to apply nu for 5 times. And if we calculate the endomorphism algebra of T, it turns out that B is isomorphic to a quotient algebra of the linear A10 quiver in this case. Yeah. So if we go a bit higher, we take D equals 3. Again, we want ND to be coprime, so we take N to be 4. So in this case, we can apply our construction. If you take the algebra A to be A53, and maybe we haven't seen this example before, but A53 is the path algebra of the following quiver here. It has 35 vertices. And I labeled the 5 vertices at the bottom left. And if you take the projective module P to be the direct sum of the indecomposable projectives at these vertices, and we get T by applying Nakayama functor and take the direct sum, then this T is the tilting complex in this case. So, and we can calculate the endomorphism algebra explicitly. It's also given by a path algebra of a quiver with relations. And the quiver is given as follows. And it also has 35 vertices. And all the squares are commutative. And there are certain zero relations at the bottom and on the top. And there are also like more complicated zero relations, which, for example, the arrow that goes from 4 to 5, 5 to 7, 7 to 8, these compositions should be 0. And other zero relations are kind of similar. And we can calculate directly that the global dimension of B equals the dominant dimension of B equals 12. So this verifies our theorem. And also B direct sum with D of B is a 12 cluster tilting module. Yes, so in other words, that this path algebra is derived equivalent with this path algebra of this quiver. Yeah. So one last question is that how do we pick up P exactly, and why do we need the condition that ND to be coprime in this case? So remember that a d-Auslander algebra of type A is given by path algebra of a quiver with relations, and the vertex set of this quiver is given by ordered sequence of cardinality D. We can reinterpret this vertex set by the lattice path of an D times N rectangle. So for example, if we take D to be 3 and N to be 4, and we draw a 3 times 4 rectangle here, and a lattice path means a path that goes from the bottom left corner to the top right corner, which only pass through those lattice points. So, for example, this path is the lattice path. And moreover, we can label each step by integers starting from 1, and at maximum, it can be n plus d. If we only collect those labelings of horizontal steps, then we would get an ordered sequence of cardinality d. And in this example is exactly 1, 4, 7. So this is how we commute between this OS n plus 1d and this LDN. Like how do we interpret an ordered sequence as a lattice path, and from a lattice path, how we get an ordered sequence. This is kind of the dictionary. So what is the advantage of introducing this new combinatorial model to the algebra? We know that all the indecomposable projectives of A, they are one-to-one correspondent to each vertex of the quiver, right? So in other words, the indecomposable projectives can be labeled instead by lattice paths of this rectangle. And of course, we want to pick up a special P. And this special P is gonna correspond to some special path in this case. So that's why we need the requirement that ND are co-prime. Because in this case, the diagonal doesn't pass through any lattice point. And so we could pick up those paths which stays below the diagonal. And they have a name, which is called rational Dyck path. And the special projective module we want to pick up is exactly the direct sum of all the indecomposable projectives that corresponds to rational Dyck path. So again, if we look at the example where d equals 3 and n equals 4, we can see that the diagonal doesn't pass through any lattice point. And there are 5 lattice paths which lies below the diagonal. And we can take their coordinate, which is like 1, 3, 5, 1, 3, 4, and so on. If we remember the example we have seen before, the algebra A we take to be A53. And then the vertex set of the quiver Q is given by all the lattice paths in this 3 times 4 rectangle. And the Dyck path consisting all these vertices, which are exactly these 5 vertices. So by introducing this combinatorial model, we have a canonical way to pick up this projective module P. And actually, remember that if we want to show that a complex is tilting, we need to prove the rigidity and also the generating property of this object. By using this combinatorial model, it actually helps with the proof of both. So, yeah. Furthermore, we get some further observations about the algebra B, also the endomorphism algebra of the tilting complex. I recall here the settings that A is a d-Auslander algebra with ND coprime, and we take P the way I just introduced, and the tilting complex. And we denote by B0 to be the endomorphism algebra of P in dB of A, and B to be the endomorphism algebra of the tilting complex T. So, as we have seen from the main theorem that we know that B has a finite global dimension and also fractionally Calabi-Yau property. But indeed, B0 also, like a much smaller algebra, B0 is also has these nice properties. So we can calculate the global dimension of B0, which is d minus k, where k is the upfloor integer of d over n. And B0 also has a fractionally Calabi-Yau property, in which the fraction is given here. Moreover, we can describe B as the n plus d replicated algebra of B0, which is matrix algebra with the diagonals B0 and the upper off diagonal to be B0 here. Yes. Moreover, we have seen that B has a ND cluster tilting module, which is given by the direct sum of projective and injective modules. So we could again calculate the d-Auslander algebra of B, which turns out to be isomorphic to the m plus d plus 1 replicated algebra of B0. So in some sense that this algebra A is rather complicated. As you go, as D grows larger, the quiver will become more complicated. But it derived equivalent to the algebra B, which is actually obtained by the replicated algebra of a smaller algebra. So we would hope that by studying the algebra B, we could gain more information about the algebra A. Yeah, so I think that's all I want to present for today. Thank you.
Wow, thank you.
Thank you.
Amazing.
Oh, I went a bit fast, maybe.
Oh, it was nice. The speed. Do you have any questions for Wei?
Yes.
Yes, please.
Yeah, thank you very much, Wei. I was very much looking forward to your talk. So, do I understand correctly that the algebra B0 that you get as a replicated algebra is the sort of the poset algebra or the incidence algebra or for the Dyck paths?
It is a quotient algebra of the instance algebra of rational Dyck path.
Ah,
Because because we have extra zero relations. Wait, let me see. Like here, right?
Okay.
Yes. Yeah.
Yes, yes. Yeah. No, because I was wondering. So there is this conjecture. I think is attributed to Frédéric Chapoton, which relates, the incidence algebra of Dyck path with the incidence algebra of the associahedron, which is also related to AN linearly oriented, right?
Yes.
So, do you think you could say something about that conjecture, or I mean, this is a quote, maybe not.
Yes. If we take D to be 2, D to be 2, and then by another result, by applying another result by Chapoton and Latcani, maybe, they could show that B0 is actually derived equivalent to the instance algebra of rational Dyck path when D equals to 2.
I see.
Yeah. And but when D equals 3, I've tried small examples. This doesn't hold. Yeah, it's not true anymore. But I didn't really check really like their conjecture, if their conjecture holds true for D equals 2 or higher or not.
Yeah, but still, it's a proper quotient. I mean, it might not still be. Okay, thank you.
Thanks.
Okay, any other questions? I have like a curiosity.
Mm-hmm.
All, there are a lot of calculations.
Yes.
And yes, okay. So it's something that you have done like by hand, like a very hard work, or do you use some software or?
Mm-hmm. I think, well, mm, they are like, because everything is given by like combinatorial data, right? Like, for
Hmm.
example, these modules, the so because we start from a projective module, when we apply Nakayama functor to it, actually we get a shifted module of this kind. Yeah, so it's kind of easier to calculate, like for example, the extension groups or of these modules, and they generate or something.
Hmm.
Yeah. So I mean to say that is doable by hand.
Okay, okay. Yeah,
Yeah.
so it's very big, but not very complicated in each step.
Yes. But
Ah,
yeah, to verify, but to really show the rigidity and generating, we do need these paths. Or else, like by just using the coordinate of the module, I don't know how to do it.
no, that's nice.
Yeah.
Thank you.
Yeah, actually, I have another question. Um,
Yes,
so for the very first example that when you speak about the
this
work,
one.
yeah, no, yeah, in the work of Herschen, Bam, and Basso, yeah.
This one. Mm-hmm.
So in that paper, you say, yeah, well, okay, in this case, they show that you have a causal dual of A, right? That B is a causal dual of A. Uh,
Mm-hmm.
is there some kind of higher causal duality that you have? Because now you, instead of having, is there a notion of higher causal duality that you could apply for the second case, for the one in Canis or yours in general?
Mm-hmm.
Maybe it doesn't exist.
I haven't thought about it in that direction, though. I don't know.
Yeah, okay.
I'm sorry. I don't know really.
Yeah,
Yeah,
because
but it's a nice question.
because for the case of yeah, then the algebras mentioned, the causal duality is really changing the relations from the place of the relations that you have.
Mm-hmm.
So maybe for this, I mean, these higher Auslander algebras are in some sense the higher version.
Mm.
So you might
Yeah.
have kind of thing like that. Especially
Yeah.
because for the case d equals 2, you change two relations to three relations, right? Relations of three.
Yeah. Yes, you mean here.
Right.
Yeah.
So you have some commutativity things that you had before, and then suddenly have
Mm.
relations which are similar to right cube.
Mm. Yeah. Yeah, I will think about it. Thank you for the question.
No, my pleasure. Very nice talk.
Thanks.
Okay. Do you have any other questions? Okay. If it's not the case, thank you again, Wei. It was a
Thanks.
very nice talk, very
Thanks.
enjoyable. Yes.